Alright, so this video is on electric potential and potential energy. Let's start by covering some of the basic topics such as what is electric potential. So electric potential, written as V, is equal to the potential energy per unit charge. And if we talk about a charge at point A, this would be VA is equal to UA over Q. However, we're more interested generally in potential difference than just potential itself. So when electric force does positive work on the charge, the kinetic energy increases and the potential energy decreases. And the difference in potential energy, which is UB minus UA, and we're just talking about a charge that moves from point A to point B, that is equal to the negative of the work WBA done by the electric force to move the charge from A to B. So that means the potential difference, which is VBA, is equal to VB minus VA equal to UB minus UA over Q, and we already know this is equal to negative WBA over Q. And we can also say that the units for potential is equal to joules over coulombs, which is equal to volts. So we can better understand electric potential by comparing it to gravitational potential energy, which is equal to mgh. So the greater the height, for example, of a cliff, the more potential energy a rock would have at the top relative to the bottom. And the amount of work depends on both the height of the cliff and the mass of the rock. So a larger rock and a smaller rock can both be at the same height, h, but the larger rock will have a greater potential energy because it has a greater mass. So in the same way, electric potential energy, it depends both on the potential difference, which would relate to the height of the cliff, and the charge corresponding to the mass. Okay, so now let's talk about the relationship between electric potential and electric field. So we know that VBA, in addition to being equal to this, is equal to negative integral from A to B of E dot dl, where E is the E field. And if you integrate this, then you can just get that VBA is equal to negative E d. And if we're talking about a point charge here, where d would be the radius, then if E, which we know from E fields, is equal to kq over r squared, or 1 over 4 pi E naught q over r squared, then VBA is equal to 1 over 4 pi E naught q over r, because this r and this r would just factor out, or would cancel out. And another way to write this equation, which we'll be using very soon, is to write it in the differential sense. So dV is equal to 1 over 4 pi E naught dq over r, and then obviously if you take the integrals of both sides, then you end up back with this equation. So this is the equation for a point charge. And now we're going to take a look at how to find the potential due to a charged disk. Okay, so as you can see, I've set up the diagram for finding the electric potential of a disk with one failed attempt, and also the equation that we found earlier. So in order to find the electric potential of the disk, we first have to find something to replace dq with. And in this case, because it's a disk, we're going to use surface charge density. So with the surface area, we know Q is equal to sigma A, but we want dq, so that's equal to sigma dA, which is because A is equal to pi A squared, area of a circle, then this is just equal to 2 pi A sigma dA. So we're going to put this whole thing in for dq here. We know the limits of integration are from 0 to big R. And I'm just going to plug this in. And we can replace r with the a squared plus x squared right there, square root of. Okay, so in solving this integral, we're first going to take out all the constants. Oops, sigma there. And we're just left with a dA over the square root of a squared plus x squared. And for this, we can just use a simple u substitution, let u equal to a squared plus x squared. Then du is just equal to 2a dA because x squared is a constant. And then dA is equal to 1 over 2a du. Plug this back into here. The two a's cancel out here. We're left with 1 over 2 root u du. So then this becomes a pretty easy integration because this is just, this would just be the square root of u. From 0 to r, substitute this back in. And then we're going to plug in 0 and r right here. And then when you do that, we end up with 2 pi sigma k out here. And then the square root of big R squared plus x squared. And then minus the square root of x squared, which just becomes 2 pi. You can say k sigma. And then the square root of r squared plus x squared, and this would just be x. So this is our electric potential for the disk. So this was just a quick refresher, I guess, on how to derive the electric potential formulas. There's a few more. Pooja's going to go over a different one in her video, and I'm sure the other ones are probably in your notes. So now we're going to move on to some problem solving. So here I've just drawn out our first practice problem. In this case, we're looking at this xy coordinate right here. There's a 1 microcoulomb positive charge 1 meter away from the origin and a negative 1 microcoulomb charge also 1 meter from the origin. So for this problem, we're going to find at the origin first the electric potential and then the energy needed to bring the 1 microcoulomb charge to this position from infinitely far away. Alright, so let's start with the first one. Electric potential, we already know, is equal to kq over r. So this is a relatively simple problem. We just have to plug in values here. So k is 9.0 times 10 to the 9th Newton meters squared over Coulomb squared. We know that Q is 1 microcoulomb, so 1. And then the distance from the charge to the origin is just 1 meter. So this is pretty simple math here. We end up with 9 times 10 to the 3rd over 1 meter, which is just 9,000 volts. So electric potential is a scalar quantity, and it doesn't have direction, but it does have a sign. So actually, although the magnitude of both electric potentials are the same, the total electric potential would be this 9,000 volts from the positive charge, and then negative 9,000 volts from the negative charge. So this actually just ends up being 0 volts. Now the second part is asking for the energy. So for part B, we already know V is equal to U electric over Q, which means delta U electric is equal to, this would be a delta V there, Q delta V. And we actually just found delta V in the previous part, which was 0 volts. So we have Q times 0, and the energy is actually 0 joules. So whenever the potential is 0, there is no work required to move the charge to that point. Alright, so this is our second practice problem right here. It's a little bit more complicated. So what's happening is that a positive charge of 2 microcoulombs is held on a horizontal plane. And then we have a negative charge of negative 1 microcoulomb. It's held 5 centimeters north of it, and then a 3 microcoulomb charge is held 5 centimeters west. So the problem is asking us to find 3 things. First, the total potential energy of the system, the potential energy of the 3 microcoulomb charge, and the speed of the 2 microcoulomb charge, assuming it has mass of 1 gram, when it is infinitely far away or very far, far away from the 2 other charges. So I just wrote all this out because it would have taken a very long time to write in real time. And basically what the first thing we're going to do is draw a diagram of the situation. So here we have the 2 microcoulomb charge, negative 1 and 3, and I just numbered these as 1, 2, and 3 for convenience. We can see that the distance between each of these 2 charges is 0.05 meters, and for this one you just find the hypotenuse, which ends up being 7.07 times 10 to the negative 2 meters. Alright, so to find the total potential energy of a system when it has more than one charge, we can use the formula U total equals KQ1 Q2 over the distance between the 2 charges. And in this case, because we have 3 charges, we also have 3 pairs, which means we also use KQ2 Q3 over R23 and KQ1 Q3 over R13. So at this point, we basically just plug in all the numbers. K again is 9 times 10 to the 9th, and then here are just each of the charges over the distance. And if you plug all that into your calculator, you end up getting 0.338 joules. So that's the first part. Okay, so for the second part, it's asking us for the potential energy of just the 3 microcoulomb charge. So if we're looking at just this one, the U total for the 3 microcoulomb would be U13 plus U23. So that's what we're going to do right here. It's very similar to the first part, but we just add up these 2 charges. Do the same thing, plug it into your calculator. I already wrote it here, so I figured it's the same thing. And then you end up getting 0.698 joules. So the last part is asking us for the speed of the 2 microcoulomb charge when it's very far away from the other 2 charges. So to find this, we're going to use the law of conservation of energy. We know that the 2 energies involved are potential and kinetic. So U initial plus K initial plus work is equal to U final plus K final. And in this case, we know both initial kinetic energy and work done is 0. So we can just rewrite this as U total is U12 plus U23 plus U13. U final, because when the 2 microcoulomb charge is very far away, it doesn't have any effect on the system. So really all we're looking at is the 3 microcoulomb and the negative 1 microcoulomb charge. So U final is actually just U13, and K final is what we're trying to figure out in this part. So we can cancel out these 2 U13s and reorder this and say K final is equal to U12 plus U23. Again, we just use the same equation right here, plug in the values, and we get that K final is equal to 0.72 joules. Now, we're not actually done yet because we're trying to find velocity and not just K final. So we know that kinetic energy is equal to 1/2 mv squared. So we can reorder that equation. V squared is equal to 2 times 0.72 joules over the mass here. We know mass is just 1 gram, or 1 times 10 to the negative 3 kilograms. So we just do the square root of both sides and plug it into a calculator. We end up with 37.9 meters per second. So that's all there is to this problem. And I hope you guys learned something from this video. Good luck with electric potential.